Have you ever wondered why a body which is dropped from some height will fall vertically downward until it hits the Earth's surface or the ground? You can see in this diagram we have a building out here, and this ball is being dropped from the top of the building. So what happened to this ball? It will fall vertically down until it reaches the ground. Or if you take the ball and you throw it in some direction upward, what will happen to the ball? The ball will go, it will reach some height, and then it will fall back down onto the ground, right? What is the reason for this? Why any body which is thrown up will always come back down? I think you know the reason, isn't it? And the reason here is because of something called gravity, or the force of gravitation. We know that the Earth always attracts a body to the center of the Earth, right? As seen from this figure here, the Earth, it is attracting this ball. So therefore, this ball will always fall back down, even if it is thrown up. Okay. But what will happen if the ball is very far, it is situated very far from the Earth, as shown in this figure? Okay, now the question is, will this ball fall back onto the Earth? Or, in other words, will the Earth be able to attract the ball so that this ball will fall back down? Alright, so to answer that question, we have to look at the universal law of gravitation. Now, according to this law, it says that the force of attraction between two bodies is given by F is equal to G, mass of the body into mass of the Earth, by distance square. Okay, what is R here? R here is the distance between the body of mass small m and the Earth of mass capital M. Now in this equation, if you look carefully, what will happen if R is large? If R is large, and since R is situated in the denominator, then F will be small. Yes or no? In fact, if R is infinite, okay, if R is very large, then let us replace here R with infinity. So you have infinity square, and that would be even larger, right? Anything divided by infinity, that is 0. So what will happen to the force here? The force here will be 0. Understand? So as shown in this figure, if the distance is very large, can you see the distance from here to the Earth? That's very large, isn't it? So that means the force with which this body is F, this will be 0. So if no force is acting on the body, do you think this body will fall to the Earth? No, this body will not fall to the Earth. Why? Because there is no force acting on it. So what will happen to this body then? If it doesn't fall back onto the Earth, then what will happen to this body? It will just float in space. Okay, it will be stuck right there in space. Got it? So from here we understand that if the body is, let's say, near enough, okay, if this body is, let's say, somewhere here, if this body is somewhere here, then will this body be able to fall onto the Earth? Yes, it can. Why? Because the distance from the body to the center of the Earth is quite small. Okay, so R here is quite small. And again, from this equation, since F is inversely proportional to R square, if R is small, then F will be large. Alright, and if F is large, then this body will be able to fall back down. Understand? So anyway you put, let's say you put a body here. Okay, you put a body here, and since the distance is still small, this body will be able to fall back onto the Earth. Got it? What about if the body is very far here? Will this body be able to fall onto the Earth? No. Why? Because F here is, it will be 0. Why F is 0? Because R here is very large. It's infinite. And if R is infinite, F will be 0. You got the idea or not? So from here, we understand that there is a region surrounding the Earth within which, if the body is inside that region, then the body will be able to fall back onto the Earth. Okay. So in this diagram, you can see there is a region surrounding the Earth. Okay, and I have a number of bodies here. Now these bodies, this one, and this one, they are within the region. That means they are situated inside of this region. This is not a cloud, mind you. All right, so this is just a space or region. In fact, you cannot see this space or region. Okay, so because these bodies are still inside, then what will happen? They are being attracted towards the earth as indicated by the white arrows. Okay, what about these bodies? This one, and this one. They are outside of this region. So will these bodies be able to fall onto the earth? No, they will not fall. This one also will not fall. This one also will not fall. So from here we understand that surrounding any planet or any body, there is a region within which, that means inside the region, if you put a second body, that second body will be attracted by the first body. And that region is nothing but the gravitational field. Okay, and this is our topic of discussion in this. So what is a gravitational field? A gravitational field is nothing but the space or region surrounding the earth or any body or any planet within which the force of attraction of the earth can be felt. It means that these bodies which are still inside, which are inside this region, only these bodies will be able to experience the gravitational pull of the earth. Once this body moves outside or it goes outside of this region, it cannot experience the gravitational pull of the earth anymore. Okay, so again let us look at the definition here. It is a space or region surrounding the earth or any body within which the force of attraction of the earth can be felt. So this field, gravitational field, it is a vector quantity or a scalar quantity. Gravitational field, just look at this, it is the space or region, all right, and because of this it is a scalar quantity, all right. But then to understand the gravitational field nicely, we have to introduce a term called the intensity of gravitational field. Now, what is the meaning of intensity of gravitational field? By intensity, we mean strength of the gravitational field. Okay, so the intensity of gravitational field at a point P in the field. That means, imagine if we have a point P which is inside of the gravitational field, then what is the strength of the field at that point? The intensity of gravitational field at a point P in the field is defined as the force experienced by a body of unit mass. Unit mass means m is equal to 1 placed at that point. It is given by I is equal to F by m naught. M naught here is a test mass, is equal to gm by x square. What is capital M here? It is the mass of the planet. Okay, and x here is the distance of point P from the center of the planet. All right, in vector form, I bar is equal to minus gm by x square into x cap. Now, what is the significance of this minus sign? This minus sign indicates that the gravitational field is directed towards the center of the earth. Okay. All right, so let us look at some important points when it comes to the gravitational field. Now, the gravitational field is a gravitational field intensity is a vector quantity directed to the center of the earth. Can you see here in this diagram, we have these arrows. Now, what are these arrows? These arrows are the pictorial representation of the gravitational field. Okay, so it's easier for us to understand the gravitational field if we draw in terms of arrows like these. And if you look at the direction of the arrows, they are always directed towards the center of the earth. All right, so because they have direction, what type of quantity are they? They are a vector quantity. Okay, what else? Its dimensional formula is same as the acceleration due to gravity. How do we know that its dimensional formula is same? You remember or not, what is the expression? F is equal to, not F, I is equal to F by m naught, isn't it? So isn't this of the form F is equal to ma, and isn't this a F by m, right? So therefore, if you compare this equation and that equation, we can clearly see that A is similar to I. Or in other words, I is similar to A. But in this case, A here is the acceleration due to gravity. So it should have the same dimensional formula as the acceleration due to gravity. And this is the dimensional formula. Inside a hollow sphere, okay, inside a hollow sphere, imagine if the Earth is hollow. Of course, the Earth is not hollow, it's solid. What is the intensity of gravitational field? That will be 0. So if we plot a graph, the gravitational field with distance for a hollow shell, we can see that if we go from the center of the shell to the surface, that means the distance r, the intensity of the field will be 0. At r, the intensity will be maximum, and then as you go away from the surface, the intensity decreases according to this relation. But for a solid sphere, like for example the Earth, okay, this is how the intensity of gravitational field varies. It goes linearly, and then till it becomes maximum on the surface, and then outside the surface it is decreasing down like this, okay, according to this variation. All right, so that is the concept of the gravitational field and the gravitational intensity of the Earth. Thank you.